Welcome to G Fun Facts Online, where we dive into the amazing world of science and technology. Today, we're talking about a material so extraordinary it sounds like science fiction: Carbyne. Imagine a chain just one atom thick, made entirely of carbon. This is Carbyne, a one-dimensional wonder that could be the strongest material ever known. Scientists predict it has mind-blowing electronic properties and super high thermal conductivity. But there's a catch. Carbyne is incredibly unstable and reactive, making it a nightmare to create and study. Think of it like trying to hold a lightning bolt. However, clever scientists found a way. They can trap these Carbyne chains inside tiny carbon nanotubes, creating something called confined Carbyne. This stabilizes it enough for us to explore its secrets. And the biggest secrets lie in its quantum vibrations, or phonons. These aren't just random jiggles. These atomic vibrations are the key to almost all of a material's properties: its electrical, optical, mechanical, and thermal behavior. Understanding how Carbyne's atoms vibrate at this quantum level is crucial if we want to use it in future tech. So how do scientists spy on these tiny, super-fast vibrations? They use techniques like Raman spectroscopy, where they shine light on the Carbyne and see how it interacts. Confined Carbyne gives off a specific signal called the C mode, which tells us about how the bonds between carbon atoms are stretching and compressing. The frequency of the C mode can change depending on Carbyne's surroundings, giving us clues about the chain itself. Things got even more exciting recently, as highlighted in a study published in Nature Communications in 2025. Researchers from the University of Vienna, combining Raman spectroscopy with advanced computer models and machine learning, started to understand some really puzzling vibrations. They discovered an incredibly strong quantum mechanical link between the vibrations of Carbyne and the nanotube it's housed in. This is wild because, classically, these two structures are electronically isolated. They don't directly share electrons. It's like they're atomic eavesdropping, talking to each other electronically through their vibrations. This connection is super strong in Carbyne because of its unique electronic makeup and its inherent instability. And it's a two-way street. Carbyne doesn't just react to the nanotube, it influences the nanotube's properties in unexpected ways. These studies also revealed that Carbyne's vibrations are anharmonic, meaning they're not simple, smooth oscillations. And this complexity is vital for accurately describing it. In fact, there seems to be a universal relationship between this anharmonicity and that C-mode frequency we talked about. So why do these quantum vibrations matter so much for how Carbyne interacts with other materials? Well, firstly, these phonons are the main carriers of heat. Carbyne is predicted to be an amazing heat conductor because its vibrations are so high frequency, and the phonons can travel a long way without bumping into things. Understanding this is key for designing tiny thermal management systems. Secondly, this atomic eavesdropping or phonon coupling can change the electronic and optical properties of both Carbyne and whatever it's interacting with. The way electrons and phonons couple in Carbyne is a big deal for its overall behavior. Thirdly, at the boundary where Carbyne meets another material, these vibrational interactions are everything. For example, in composites made of Carbyne and metal, like nickel, charge can transfer between them, changing Carbyne's bond structure and the composite's strength. Scientists have even found that putting a graphene sheet between Carbyne and metal can boost the stiffness of these nanocomposites. Fourthly, because Carbyne is so stiff and strong, it's a fantastic candidate for reinforcing other materials. Its vibrations determine how it handles stress and transfers loads when mixed into something else, like a polymer, making the whole thing stronger. And finally, Carbyne's vibrations are incredibly sensitive to its environment. Things like strain, temperature, and how it's confined. This sensitivity makes it perfect for developing new types of sensors. Now, making long, stable Carbyne chains is still tough, but by confining it in carbon nanotubes, scientists have made chains up to 6,000 carbon atoms long. This has allowed them to actually test some of its amazing properties. Raman spectroscopy, especially an advanced version called tip-enhanced Raman scattering or TERS, has been the star player, letting researchers study phonon dynamics at the single chain level and even figure out properties like heat capacity. On the theory side, powerful computer simulations using methods like density functional theory have predicted Carbyne's incredible strength, its electronic properties, sometimes it's a conductor, sometimes a semiconductor, and how its atoms vibrate. These calculations also help us understand important details, like how strain affects it, and why those complex anharmonic vibrations are so important. Molecular dynamics simulations also show that its vibrational frequencies can be extremely high, up to around 6 terahertz for very short chains. So what could we do with Carbyne, thanks to these amazing vibrational interactions? The possibilities are thrilling. Think ultra-sensitive nanomechanical resonators and sensors, perhaps local temperature sensors for tiny devices. Its tunable electronic properties could lead to new nanoelectronic components, maybe even for atomic scale circuits or magnetic semiconductors. Its fantastic thermal conductivity could be used to manage heat in tiny electronics. As a reinforcement agent, it could lead to next-generation composites with unparalleled strength. The strong interaction between light and Carbyne's vibrations might even be useful for quantum information processing. And like other carbon nanomaterials, its incredibly high surface area could be great for energy storage in batteries and supercapacitors. Of course, there are still big challenges. Making long, stable, and perfect Carbyne chains is tough, even inside nanotubes. Precisely looking at these one-dimensional chains requires incredibly sophisticated tools, and the quantum mechanical dance between Carbyne and other materials is complex and needs more research. But the ongoing exploration of Carbyne's quantum vibrations is constantly revealing new wonders. The discovery of strong vibrational coupling and its universal anharmonicity highlights just how intricately Carbyne interacts with its world. As scientists get better at making and studying it, understanding these quantum whispers will be key to turning Carbyne's extraordinary promise into real-world technologies. From supersensors to incredibly strong materials and new quantum devices, Carbyne's vibrating atoms are truly setting the stage for a new era in materials science. Thanks for tuning into Fun Facts Online.